In 1980, when IBM quietly began searching for software for the personal computer taking shape inside the company, the established operating system name in microcomputing was Gary Kildall's Digital Research. CP/M had spread across a market otherwise divided among machines from many manufacturers, giving users something still unusual in the young personal computer industry, a familiar software environment that could survive a change in hardware. By that year, versions of CP/M were running on roughly 200 different computer models, and an expanding collection of business and productivity applications had grown around them. Microsoft was already an important software company, particularly in programming languages, but it did not possess the operating system IBM needed for its new machine. When IBM approached Bill Gates, the path led instead toward digital research. That made sense at the time. Kildall was not an obscure engineer waiting for a large corporation to notice his work. He had helped create the operating system model around which much of the early commercial microcomputer market was already organizing itself. Digital research had customers, software developers had learned to target CP/M, and computer manufacturers could offer access to that software without inventing an entirely separate operating environment for every new machine. IBM was therefore approaching a company that appeared to occupy exactly the position Microsoft would later become famous for holding. Nothing about that moment made the eventual outcome inevitable. The complication was that IBM's project was arriving during a technological transition. CP/M's enormous success had developed around the 8-bit Intel 8080 and compatible processors, such as the Z80, while the computer IBM was designing belonged to a newer processor generation. Digital research was already moving CP/M toward that world, but IBM was building its machine on an unusually compressed schedule and needed more than a respected operating system name. It needed software, technical commitments, and business terms capable of arriving with the hardware. Those pressures had not yet turned digital research into a loser or Microsoft into the obvious alternative. At the beginning of IBM's search, the balance still appeared to favor Kildall. CP/M had the installed base, the application ecosystem, and years of experience making software useful across machines from different manufacturers. Microsoft, meanwhile, would eventually dominate the very market IBM was about to create, even though it had entered the discussion without the operating system that would carry its name through the next decade. That is the paradox at the center of this story. The question is not why IBM went looking for Gary Kildall. Given the microcomputer market of 1980, that was entirely understandable. The question is how the operating system pioneer who appeared best positioned to enter IBM's new machine watched the standard move elsewhere. To understand why digital research seemed so difficult to displace in the first place, the story has to return to the technical idea that had allowed CP/M to spread so widely. Kildall had found a way to make the operating system depend less on one particular computer and more on a common software architecture. Gary Kildall's advantage in 1980 had been built years earlier, when the microcomputer itself was still an awkward combination of processor boards, terminals, paper tape, and newly emerging floppy disk hardware. In the early 1970s, Kildall was working with Intel microprocessors and developing tools such as PLM, a high-level language intended to make programming those processors less dependent on assembly code written for one particular machine. Around 1974, that work led him toward the operating system that became CP/M. Its first purpose was practical. Kildall wanted software capable of controlling a floppy disk system attached to an Intel 8080-based computer, but the problem quickly widened. Microcomputer manufacturers could use similar processors while surrounding them with different disk controllers, terminals, memory arrangements, and peripheral hardware. An operating system tied too closely to one of those machines would have to be reworked every time the hardware changed. CP/M gradually moved in another direction. Much of the operating system could remain stable, while the routines most dependent on the machine were isolated closer to the hardware. That idea became especially important in 1976 when Glenn Ewing approached digital research about adapting CP/M to IMSAI equipment. Kildall had already dealt with several hardware-specific versions, and had little reason to keep rebuilding the same portions of the operating system each time another computer appeared. Working with Ewing, he separated much of that machine-dependent code into a distinct layer called the BIOS, the basic input-output system. File handling, program execution, and the broader operating environment could remain largely unchanged above it. While the BIOS absorbed many of the differences required to make CP/M work with a particular computer's console, disk system, and other basic devices, the significance of that separation was easy to miss because the BIOS itself was relatively small. Its value came from what no longer had to change. A new hardware design did not necessarily require digital research to redesign CP/M from the beginning. Instead, much of the adaptation could be concentrated in the interface between the operating system and the machine beneath it. That gave CP/M an unusual degree of portability for the period. The result was not perfect hardware independence in the modern sense. Different CP/M systems still varied in memory, displays, peripheral capabilities, disk formats, and many other practical details, and software that reached around the operating system could still expose those differences. But the architecture reduced how much of the software environment had to be reinvented whenever another 80R80 or Z80 class computer entered the market. Kildall had effectively moved an important part of compatibility away from the physical machine and into a reusable software layer. That decision would become much more valuable than the original floppy control problem suggested. Once CP/M could travel across hardware from different manufacturers, the operating system was no longer useful only because of what it did by itself. Its real power would come from what programmers and customers began building on top of that common foundation. Once CP/M could move from one manufacturer's hardware to another, something began to form around it that was more valuable than the operating system alone. Programmers no longer had to assume that an application written for one CP/M computer would remain trapped on that particular machine. If another manufacturer adapted CP/M successfully, much of the same software environment could move with it. In a microcomputer market still divided among different keyboards, displays, disk systems, memory configurations, and physical designs, that common layer gave developers a larger audience than most individual hardware companies could provide. By the late 1970s, the consequences were becoming visible. WordStar, introduced for CP/M, gave businesses a practical reason to care about operating system compatibility rather than only processor speed or hardware features. Databases, accounting programs, communications packages, programming tools, and other applications added still more reasons to choose a machine that could enter the same software world. CP/M was becoming valuable because users knew what they could run on it, and that familiarity made manufacturers increasingly interested in supporting it. The relationship reinforced itself without requiring every CP/M computer to look alike. A manufacturer could build a machine around its own hardware choices, while still offering customers access to software they might already recognize from another system. For programmers, that meant a successful application had a chance to travel through the market as CP/M itself spread. The strength of that attraction became particularly clear in 1980, when Microsoft introduced the Z80 soft card for the Apple II. But Apple's computer used a completely different processor architecture, yet the add-in card gave it a Z80 and access to CP/M software. Users were effectively adding another processor to an already successful computer because the applications available in the CP/M environment were worth reaching. WordStar became one of the most prominent examples. The significance was no longer simply that Kildall had designed a portable operating system. Portability had created a commercial meeting place between hardware manufacturers, software developers, and customers who otherwise might have remained divided among incompatible machines. CP/M did not eliminate those differences. Programs that depended on unusual display hardware, disk formats, or machine-specific behavior could still encounter limitations, and no two computers became identical merely because both could boot the same operating system. But enough of the software environment remained common that CP/M could function as something the early microcomputer industry badly needed, a recognizable platform larger than any one hardware product. By the beginning of the 1980s, digital research had reached a position that would have seemed extraordinarily difficult to dislodge only a few years earlier. CP/M had become the de facto operating system standard across much of the commercial microcomputer market, supported by applications whose value reinforced the platform beneath them. The architecture Kildall had created to escape dependence on one machine had succeeded precisely because so many different machines could participate. Yet that success had developed around a particular generation of microprocessors. As the industry began moving beyond that generation, digital research would have to carry its software ecosystem across one more transition, and this time, the computer waiting on the other side would come from IBM. IBM's new personal computer arrived at exactly the moment when CP/M's dominance had to cross into a different processor generation. During 1980, a small team in Boca Raton was trying to create the machine far more quickly than IBM's traditional development methods normally allowed. Building every major component internally would have taken too long, so the team relied heavily on commercially available technology. For the processor, IBM selected Intel's 8088, a member of the newer 8086 family that could address far more memory than the 8-bit processors around which the CP/M market had developed. Its 8-bit external data bus also allowed IBM to build a less expensive system around existing support hardware. The decision made sense for the computer IBM wanted to ship, but it introduced a software problem. The enormous body of CP/M applications written for Intel 8080 and Z80 class machines could not simply be moved onto the 8088 and executed unchanged. The new processor used a different instruction architecture. Digital Research was already addressing that transition with CP/M86, so Kildall's ideas were not becoming obsolete, and his company had not ignored the 16-bit future. What IBM changed was the urgency of reaching it. The company did not want an operating system at some undefined point after the hardware was finished. Software had to become part of the product, while the machine itself was still moving rapidly toward completion. Microsoft was already involved because IBM needed programming languages, including BASIC, an area in which Bill Gates' company had built considerable experience. But when the discussion turned to an operating system, Microsoft did not yet have the product IBM required. Gates directed the IBM team to Digital
IBM needs to
Research.
license.
At that moment, the referral confirmed how strong Kildall's position still appeared. CP/M was the established standard, Digital Research understood the operating system business, and CP/M86 represented the logical attempt to carry that standard onto Intel's new processor generation. Yet the transition temporarily weakened one of CP/M's greatest advantages. The software ecosystem that had accumulated around the 8-bit platform could not automatically transfer its full weight to IBM's machine on the first day. Applications would have to be adapted for the newer processor environment, leaving the emerging 16-bit market more open than the mature CP/M world it was beginning to replace. Digital Research still brought years of experience, relationships with developers, and the strongest operating system reputation in commercial microcomputing. But those advantages now had to be converted into a product suitable for one particular machine on IBM's timetable. For IBM, past market leadership mattered less than whether the necessary software and agreements could come together while the computer was being prepared for launch. Nothing had yet predetermined which company would dominate the operating system beneath the IBM PC. Microsoft still lacked one of its own, and CP/M86 remained an entirely credible candidate. IBM had even been sent directly to the company most closely associated with microcomputer operating systems. The next step should have been straightforward. IBM and Digital Research needed to reach an agreement. Instead, their meeting in Pacific Grove became the source of one of the most persistent legends in the history of personal computing. The meeting between IBM and Digital Research would eventually become one of the most durable legends in computer history. In its simplest form, Gary Kildall went flying while IBM arrived to negotiate for CP/M, missed the meeting that could have made him the operating system supplier for the IBM PC, and left Bill Gates to take the opportunity instead. It is a memorable story because it reduces an enormous change in the computer industry to one careless afternoon. The events in Pacific Grove were considerably more complicated. When IBM's representatives arrived at Digital Research in 1980, Kildall was away, having flown his aircraft to Oakland to meet an important customer. His absence did not leave IBM standing at a locked door. Dorothy McEwen, Kildall's wife and co-founder of Digital Research, met with the visitors along with company attorney Jerry Davis. The morning involved negotiations over IBM's non-disclosure agreement, an unsurprising concern given that the personal computer project itself was still confidential. Kildall returned that afternoon, as planned, and joined the technical discussion. The future of CP/M, therefore, did not disappear because its creator refused to speak with IBM. The harder problem emerged when the two companies tried to agree on how IBM would obtain the operating system. According to Davis's later account, IBM wanted to purchase CP/M outright, while Digital Research preferred a royalty arrangement in which it would be paid for each copy. That difference mattered because CP/M was already the foundation of a successful business, serving many manufacturers. Digital Research was not negotiating over an experimental program whose value depended entirely on IBM adopting it. Giving one customer outright ownership had very different implications from continuing the licensing model through which CP/M had already spread across the microcomputer industry. IBM, meanwhile, was trying to complete a new computer on an unusually demanding schedule and needed an operating system agreement that could become part of that project. The discussions ended without a deal. Even then, Kildall apparently did not believe the opportunity had vanished. He later attempted to renew negotiations, suggesting that he regarded the disagreement as something that might still be resolved. IBM did not respond. In later retellings, the complexity of those negotiations largely disappeared. The airplane remained because it supplied the story with a perfect dramatic mistake. One man chooses to fly, another stays at his desk, and an industry changes hands. But the surviving accounts point instead to a failed business negotiation involving confidentiality, ownership, licensing, and financial terms during a moment when IBM was moving quickly and Digital Research already had an established market to protect. Later recollections differ on some details, so no single reconstruction should be treated as a transcript of everything said in the room. What matters is that Kildall did meet with IBM. Technical discussions occurred, and the two companies still failed to reach the agreement that would put CP/M at the center of IBM's new computer. That failure did not immediately destroy Digital Research, nor did it automatically hand the market to Microsoft. IBM simply still had the same practical problem it had brought west in the first place. The PC needed an operating system. Microsoft still did not own one suitable for the job. But elsewhere in the Seattle area, another company had already needed software for Intel's new 16-bit processors badly enough that one of its programmers had begun writing an alternative. His name was Tim Paterson. Microsoft's opportunity began with a problem that had nothing to do with IBM. Seattle Computer Products, a small hardware company near Microsoft, was building boards around Intel's new 8086 processor and needed an operating system that would make those machines useful. Digital Research was developing CP-M86 for the same processor generation, but it was not available when Seattle Computer Products needed software for its hardware. Programmer Tim Paterson therefore began writing an alternative. The first version appeared in 1980 under the deliberately unglamorous name QDOS, for Quick and Dirty Operating System, and later became 86DOS. Paterson was solving an immediate engineering problem, but he understood that the existing CP/M software world represented something worth preserving. Programmers already knew CP/M's conventions, and applications written for that environment would be easier to move on to 16-bit hardware if the new operating system presented familiar interfaces. Paterson used Digital Research documentation as a guide to important aspects of that programming environment, giving 86DOS a recognizable resemblance to CP/M without reproducing CP/M's internal implementation. That resemblance later fueled accusations that DOS had simply been copied from Kildall's work, but source code analysis has not supported that claim. What mattered to Microsoft in late 1980 was far more immediate. 86DOS existed, ran on Intel's new processor family, and could potentially be adapted to the computer IBM was trying to finish. After the Digital Research negotiations failed to produce an agreement, Microsoft licensed 86DOS from Seattle Computer Products in December 1980. At first, it was an arrangement that gave Microsoft access to software it urgently needed, rather than ownership of the operating system itself. Engineers then began adapting it for IBM's hardware, and Paterson later joined Microsoft, working directly with IBM engineers in Boca Raton as the system moved toward completion. By July 1981, the first version of PC-DOS was ready for the IBM machine. Microsoft had also recognized that control of the underlying operating system might become more valuable than simply supplying one copy to one customer. It purchased the remaining rights to 86DOS from Seattle Computer Products, securing the ability to develop and license the software beyond IBM. That decision created an important difference between Microsoft's relationship with IBM and the kind of arrangement Digital Research had resisted. IBM could sell its version as PC-DOS, but Microsoft did not give up the operating system itself. The same software family could be offered elsewhere under the MS-DOS name. No one yet knew how important that freedom would become. IBM's personal computer had not even been announced, and the vast compatible machine market that would later surround it did not yet exist. The immediate achievement was simply that Microsoft had solved IBM's scheduling problem. A company that had entered the discussion without an operating system had found one elsewhere, secured the rights it needed, and helped turn it into software ready for IBM's new computer. Digital Research had not vanished from the contest. CP/M86 was still coming to the 16-bit market, carrying the reputation of the operating system that had dominated the generation before it. But when IBM unveiled the personal computer in August 1981, Microsoft's operating system would already be positioned as the inexpensive, readily available option associated directly with the machine. CP/M86 would reach the same platform under very different conditions, and the difference between those two paths would begin changing the balance of the operating system industry. When IBM announced the personal computer on August 12, 1981, the operating system contest entered a new phase. But Microsoft and Digital Research did not arrive at the starting line together. PC-DOS was already part of IBM's plan for the machine. Microsoft had adapted the operating system obtained from Seattle Computer Products, and IBM customers could buy DOS as the straightforward software foundation for the new computer. Digital Research still had a route onto the platform, but CP/M86 would follow later. After Gary Kildall learned how closely some of DOS's programming interfaces resembled those documented for CP/M, he confronted IBM over what he believed was an infringement of Digital Research's rights. The dispute did not produce a lawsuit. Instead, IBM and Digital Research reached an arrangement that allowed CP/M86 to be adapted and offered for the IBM PC. That gave Kildall another opportunity to bring the operating system name that had dominated the previous microcomputer generation into IBM's new 16-bit world. By the time the IBM PC version of CP/M86 reached customers in 1982, however, DOS had already gained something Digital Research could not easily recover: time inside the market. IBM PCs were shipping, Users were beginning to build their working environments around DOS, and software developers could already see which operating system had arrived first with the machine. Then came an even more visible disadvantage. IBM listed PC-DOS at about $40, while CP-M86 was offered at roughly $240. The difference was extraordinary for two operating systems competing on the same computer. CP/M carried the reputation of the platform that had unified much of the earlier microcomputer industry, but a customer purchasing an IBM PC now had to pay several times more to choose it. Even CP/M's famous software inheritance could not transfer intact. Programs written for 8080 and Z80-based CP/M systems still had to be adapted for the newer processor architecture. So CP/M86 did not instantly deliver every advantage accumulated during years of 8-bit dominance. DOS required a new generation of software too, but it was already the inexpensive operating system most closely associated with IBM's machine. That combination of availability, price, and placement began changing developer priorities. Each customer who chose DOS enlarged the audience for DOS applications, giving software companies another reason to support the environment IBM PC buyers were actually using. It was not evidence that DOS was inherently superior to CP/M86, nor can the outcome be reduced to the price difference alone. Digital Research was confronting several disadvantages at once. Its version arrived later on the IBM PC. Much of its old application library needed conversion, and IBM presented its operating system at a dramatically higher retail price. The standard Kildall had spent years building was therefore entering the most important new personal computer from behind, rather than from the position of strength it had enjoyed before IBM appeared. Even this did not yet explain the scale of Microsoft's eventual victory. IBM could sell only the computers IBM manufactured. Microsoft had retained the right to sell its operating system to others, and in 1982, other manufacturers began demonstrating that the IBM PC itself could be reproduced. Once that happened, every new compatible machine had the potential to carry Microsoft's operating system into another part of the market. The value of Microsoft's licensing position became much clearer once IBM stopped being the only company capable of selling an IBM-compatible computer. In 1982, Columbia Data Products introduced a machine engineered to reproduce the IBM PC environment closely enough to run the software being written for it. Compaq followed with a portable in 1983 and demonstrated how commercially powerful that idea could become. Its machine offered customers access to the IBM PC software world in a transportable computer IBM itself did not sell in the same form, and Compaq licensed Microsoft's operating system for the job. The significance for Microsoft was not that another hardware company had simply chosen DOS. It was that the growing number of IBM-compatible manufacturers did not divide the operating system market into a collection of unrelated platforms. They were deliberately trying to preserve enough of the same environment that software written for the IBM PC would continue to work. Hardware brands could multiply while the software target remained recognizable. That gave MS-DOS a path very different from the one DOS would have followed if it had remained confined to IBM machines. A company competing directly against IBM for computer sales could still become another Microsoft operating system customer. As compatible manufacturers entered the market, Microsoft could supply versions of MS-DOS to them without requiring those machines to carry the IBM name. Each successful system therefore had the potential to enlarge the same DOS software environment, rather than create a separate one from the beginning. There was an historical irony in this. CP/M had originally become powerful because Kildall designed it to travel across computers from many manufacturers. Microsoft was now benefiting from software, spreading across many manufacturers as well, but this time, those machines were increasingly organized around compatibility with a common reference architecture. A developer targeting the IBM-compatible DOS environment could potentially reach customers buying computers from IBM, Compaq, Columbia, and the expanding group of manufacturers following the same standard. That made compatibility valuable not only to users, but also to software companies deciding where to invest their development effort. Business customers reinforced the pattern because they increasingly cared about preserving applications, files, peripherals, and working routines when purchasing a new machine. A manufacturer could offer different performance, packaging, pricing, or features, but abandoning the established software environment carried a growing cost. Microsoft benefited every time compatibility became part of the purchasing decision. Digital Research could still license CP/M86, and the company remained active in operating system development, but it was no longer receiving the strongest growth from the architecture, transforming the business computer market. The momentum around IBM-compatible machines was increasingly becoming momentum around DOS as well. By the middle of the decade, Microsoft's operating system was no longer important merely because IBM had selected it for one successful computer. It was becoming a common software layer across competing manufacturers whose success collectively enlarged the platform. Kildall had once shown that an operating system could unite machines built by different companies. Now, that same basic economic power was operating on a much larger 16-bit market. While digital research found itself outside the center of the standard, it had helped teach the industry to value. The question was no longer whether CP/M had mattered. It was what digital research would do after the market it once dominated had begun organizing itself around something else. Losing the center of the IBM PC operating system market did not make digital research disappear. Through the 1980s, the company continued developing software around ideas that went well beyond the relatively simple single-user environment of early CP/M. MPM had already extended Kildall's operating system family toward multi-user computing, while later systems such as concurrent CP/M and concurrent DOS explored multitasking and compatibility across changing software environments. Digital Research remained a substantial international software company, employing hundreds of people at its peak and continuing to develop technology long after DOS had begun displacing CP/M as the center of personal computing. What had changed was the position from which those products entered the market. During CP/M's rise, digital research had helped define the environment other companies wanted to support. As the IBM-compatible market expanded, the company increasingly had to introduce new ideas into an ecosystem whose strongest commercial momentum was already forming around Microsoft's operating system. That did not stop digital research from taking ambitious directions. In the mid-1980s, GEM, the graphics environment manager, brought a graphical desktop, menus, icons, and windows to computers, still commonly associated with text-based DOS interfaces. GEM appeared on multiple systems and became the graphical environment behind applications such as desktop publishing software, showing that digital research could still influence how people interacted with personal computers even when CP/M was no longer the dominant standard. Later in the decade, the company confronted Microsoft more directly. DOS, first released in 1988, offered compatibility with the DOS software environment, while competing through features and implementation choices of its own. The reversal was striking. Digital research had once possessed the platform other software companies adapted themselves to. Now it was producing an operating system designed to enter a market whose compatibility expectations had largely been shaped around DOS. Kildall's own interests were moving in other directions as well. Rather than spending the rest of his career trying only to recover CP/M's former position, he pursued technologies that pointed toward new ways of distributing and organizing information. Through ActiVenture, later renamed KnowledgeSet, he and his collaborators explored optical storage at a time when putting enormous bodies of reference material onto a compact disk was still an unfamiliar idea. In 1985, that work helped place Grolier's Academic American Encyclopedia onto CD-ROM, anticipating a form of electronic publishing that would become commonplace years later. Projects such as this make the familiar image of Kildall as a man whose career ended with IBM especially misleading. Digital research remained active. Kildall continued experimenting with technologies beyond operating systems, and the company he had helped build survived until Novell acquired it in 1991. What had changed was not his ability to create software or recognize important ideas. It was the location of the industry's center of gravity. CP/M had once given digital research extraordinary influence because manufacturers, developers, and customers increasingly organized themselves around its software environment. By the later 1980s, that organizing force belonged primarily to the IBM-compatible DOS platform. Kildall had lost the dominant standard, but the ideas that had made CP/M important, portable software environments, hardware abstraction, and an ecosystem capable of spanning machines from different manufacturers, had not disappeared with it. That leaves a more interesting final question than whether one missed meeting cost him everything. When Microsoft carried those same broad principles into a much larger PC market, how much of the revolution it dominated had actually begun with Gary Kildall? By the end of the 1980s, there was no longer much doubt about which operating system had captured the center of the IBM-compatible PC market. DOS had become the environment around which manufacturers, developers, and business customers increasingly organized themselves, while CP/M was remembered primarily as the standard of an earlier microcomputer generation. The harder question was what that reversal actually said about Gary Kildall. Return to 1980, when IBM first began searching for software for the machine that would become its personal computer. Digital research appeared to possess almost every advantage an operating system company could want. CP/M was established across hundreds of machines. Software developers already knew the platform, and Kildall had years of experience making one operating environment work across hardware from different manufacturers. Microsoft entered IBM's search without the operating system the company needed, yet the advantage did not survive the transition intact. IBM arrived while the industry was moving from the 8-bit processors that had supported CP/M's rise into a newer 16-bit generation. Digital Research and IBM failed to reach a business agreement. Microsoft found an available operating system at Seattle Computer Products, adapted it for IBM's machine, and retained the ability to license its own version elsewhere. DOS reached IBM PC customers first. PC DOS was offered at a far lower price than CP-M86, and then compatible manufacturers began multiplying the number of computers capable of joining the same software environment. No single one of those events explains the outcome by itself. Together, they shifted the place where the industry's momentum accumulated. That is why the familiar story of Kildall losing everything because he went flying on the wrong day is so unsatisfying. It turns a structural change in personal computing into a personality lesson and misses what Kildall had already accomplished before IBM ever appeared. CPM had demonstrated that an operating system could become valuable precisely because it was not confined to one computer manufacturer. Separating machine-specific routines into the BIOS made the system easier to adapt across different hardware, and that portability gave software developers access to customers using many kinds of computers. The result was one of the earliest substantial independent application ecosystems in microcomputing. What happened in the IBM-compatible era did not make those ideas irrelevant. It revealed how much more powerful the economics of a common software environment could become when combined. With an architecture that manufacturers reproduced on an enormous scale, IBM supplied the reference machine and commercial credibility. Compatible manufacturers expanded the hardware market. Developers followed the installed base, and Microsoft happened to control an operating system it could license across that expanding field. Digital Research therefore lost something historically enormous. The chance to remain the dominant operating system supplier as personal computing moved into its next mass market generation. But Kildall's place in that history should not be measured only by the company that eventually overtook him. Years before DOS became the center of the PC world, he had already demonstrated that software could become more important when it traveled across machines rather than remaining trapped inside one manufacturer's hardware. The market that later made Microsoft powerful would operate on a far greater scale, under different technical and commercial conditions, but it rewarded the same fundamental expectation that users and developers increasingly valued: a stable software environment capable of surviving changes in the computer underneath it.